if the mass of the moon is m by 81, where m is the mass of the earth, find the distance of the point where the gravitational field due to earth and moon cancel with each other from the center of the moon. Given that the distance between the centers of the earth and moon is 60 r, where capital R is the radius of the earth. So basically we have to find the position of the null point. Null point is wherein the gravitational fields of two objects cancel out along the line joining them. So that null point is to be found out. The distance of that null point is to be found out from the center of the moon, and the options are 4r, 8r, 12r and 6r. Let us start. So the distance between the center of the moon and the center of the earth is 60r, and outside these spheres they behave like point masses. And what is the expression for the gravitational field? E subscript G, G, they are all one and the same thing. Gravitational field intensity, gravitational field, again one and the same. So let us say that point at which the gravitational fields due to moon and earth cancel is point P, and it is at a distance of r, small r, from the center of the moon. And from what is given, the distance from the center of the earth will be 60 capital R minus small r, right? So at point P, these fields should cancel, correct? So the gravitational pull of moon will be towards its center, and the gravitational field of earth will be towards its center. So let's call them as E1 and E2 respectively. And at P, the net gravitational field must be 0. So E1 and E2 should be equal in magnitude and opposite in direction. So the magnitudes must be equal, opposite in direction taken care of. So I must have E1 is equal to E2. What is E1? Well, it is G times mass of the moon, which is m by 81, and the distance from point P is r, so it will be r squared. Here m is the mass of the earth, so mass of the moon is m by 81 as provided in the problem. Must be equal to in magnitude to what? E2, the gravitational field of earth. So Gm by, the distance is 60r minus small r whole squared. Now we have to calculate the value of small r. So let us start. Gm gets cancelled. So I'll have 1 by 81 r squared is equal to 1 by 60 r minus small r whole squared. Let's take the square root. So I'll have 1 by 9r is equal to, since I have taken the square root, it will be plus or minus 1 by 60 capital R minus small r, right? So let us solve. I'll have 60 capital R minus small r is equal to plus or minus 9r, correct? So now I'll have 60r is equal to minus 8r, or 60r is equal to 9r plus r, which is 10r. Agreed? So this is gone because r is a distance that we have defined. Either it should be 0 or positive. It can't be negative. So the negative value can be neglected, ignored. So I'll be left with 60 capital R is equal to 10r, which gives r is equal to 6r. This is the distance from the center of the moon at which the gravitational field of earth and moon cancel with each other, or in other words, this is the position of the null point between moon and earth. So the answer is 6 times capital R, and which is the option that supports this result? It is option D. A thin rod of length L is bent to form a circular ring. Its mass is capital M. What force will act on a mass small m placed at the center of that circular ring? That's the question. And the options are 4 pi square G capital M small m by L square, GMM by 4 pi squared L squared, 2 pi G capital M small m by L squared, and 0. So let us see which of the option is the correct one. Let us start solving. So what we have initially is a rod, a thin rod, and now it is bent to form a circular ring. And at the center of the ring, we place a mass small m, and we want the net gravitational force at the center of the ring. So in order to do so, what I'm going to do is I'm going to consider two elements, two arc elements, which are identical in size and located diametrically opposite to each other. Okay. So they are located diametrically opposite to each other. Now what I'll do is I'll calculate the net force due to these two elements which are diametrically opposite and then continue the analysis. So let us divide this ring into two halves, the upper half and the lower half. So from symmetry, I have taken one element from the upper half and the diametrically opposite element from the lower half. Now, dm is the mass which gravitationally attracts m at the center on the either of the elements, correct? So the m will experience an attractive force df due to element 1 and df due to element 2 in the opposite direction. Correct? Why I have written the same force df? Because masses are the same, distance is also the same. Distance is nothing but the radius, isn't it? So now you can see that one df is equal and opposite to the other because the elements are diametrically opposite. So they will cancel and the net force due to these two elements will be 0. Similarly, for every element you choose in the upper half, one can always consider an identical element, diametrically opposite identical element in the lower half, such that the force due to both of them cancel out. Which means, effectively, the force due to the upper half of the ring and the lower half of the ring cancel out, making the net force on mass m placed at the center 0. That's the required answer. The net force is 0. And which is the option that supports that answer? It is option D. A spherical shell is cut into two pieces along a chord as shown in the figure. P is a point on the plane of the chord. The gravitational field at P due to the upper part is I1 and that due to the lower part is I2. What is the relation between them? And the options are I1 is greater than I2, I1 is less than I2, I1 is equal to I2 in magnitude, and D, no definite relation. Right? So what they have given, since the gravitational field is a vector, this I1 and I2 they have given are basically the magnitudes of the gravitational field intensity vector. Right? P is a point on the chord, so P is a point inside the shell. So the most important relation you need to know in order to solve this problem is that whenever you have a shell, right, a hollow sphere, the field inside a hollow sphere, the gravitational field inside the hollow sphere is always 0, right? So this comes from the direct result in gravitation, the fact that the field inside a shell is 0. A uniform shell is 0. So if the net field is 0, the net field at a point P is due to 1 and 2, correct? Due to the part of the shell 1 and the other part 2. So now both of them will contribute to the gravitational intensity at point P. And if the corresponding gravitational intensities are I1 and I2, they should always add up to 0. Or in other words, the field due to 1 must be equal and opposite to the field due to 2. Now if you take the magnitudes, so I'll have magnitude of I1 is equal to, when I take the modulus of minus I2 vector, it is just I2, the magnitude. So the two magnitudes must be equal. Only then will the field inside a shell be 0, which is a requirement because that's a very well-defined result in gravitation. The net gravitational field inside a shell is always 0. At all points inside the shell is always 0. So that's the required answer. The two magnitudes must be equal. Right? So which is the option that agrees with this result? Yes, sir, it is option C. The gravitational field in a region is given by Eg vector is equal to 4I cap plus j cap Newton per kg. Work done by this field will be 0 when the particle is moved along the line, and the options are y plus 4x is equal to 2, 4y plus x is equal to 6, x plus y is equal to 5, x minus y is equal to 5. Okay, so how do we do that? Well, the gravitational field, you look at the units, it's Newton per kg, so it is force per unit mass. Nonetheless, it is the force acting on a unit mass, isn't it? So, work done by the force is what? Force into displacement. We want this work done to be what? The problem says it has to be 0. If the work done by the force has to be 0, then the force and displacement must be perpendicular to each other, which means the straight line along which the particle in question is moving must be perpendicular to the gravitational field vector. Only then the work done will go to 0. That's the idea you have to have in your mind in order to attempt this question, right? So let us start. So here are the options once again. There's a reason why I have retained the options in the slides. You will come to know in a moment. So the first thing is we have a gravitational field vector. Both the components are positive, 4I cap plus 1j cap. So it's in the first quadrant. That's why I written the vector in that particular sense. And if this is the x-axis, and if this angle is theta, then tan theta will be the angle made by this gravitational field vector with the x-axis, and it will also be the slope of the line along which this particular vector exists, right? Now the particle has to get displaced in a line perpendicular to this, only then the work done will be 0, right? So the particle has to get displaced along a line perpendicular to it, and let's say this line is of the form y is equal to mx plus c. I'm writing it in the slope intercept form, and m here is the slope, c here is the y-intercept, right? So the slope of the line along which EG is present and the slope of the line y is equal to mx plus c must be in such a way that their product must be -1, right? So whenever you have two straight lines which are perpendicular to each other, the product of their slopes must be -1. This is a result coming straight out of straight lines coordinate geometry from your mathematics classes, right? So now what is the slope of EG, or the line along which EG is present? It is tan theta, and we know that from vectors tan theta is nothing but the y component divided by the x component. Y component is 1, x component is 4, so tan theta, or the slope of EG, or of the line along which EG is present, is 1 by 4. The slope of the line that we have considered is m, so we must have m into 1 by 4 is equal to -1. M into 1 by 4 must be equal to -1, which implies m must be -4. So the straight line that we are searching for must have a slope of -4. So let us see which of the options give you that. I'm going to rewrite all these options in the form y is equal to mx plus c, and whichever line has m equal to -4 is the culprit and our answer. So let us see that. So first option, y is equal to -4x plus 2, right? Second option, y will be equal to, x goes to the other side, so it is minus x by 4 plus 6 by 4, which is 3 by 2. Third option, y is equal to minus x plus 5. And fourth option, will be y is equal to x minus 5. So all of them are in the form y is equal to mx plus c. So let us quickly identify the m's, the slopes. For the first option, m is minus 4, and this is what we require, right? But let's complete the question. Second option, y is or m is minus 1 by 4. Third option, m is minus 1, and fourth option, m is 1. So which is the option that satisfies the result or the fact that the slope of the straight line must be minus 4? Yes, it is option A. And this is how you solve this particular problem. So we are looking for the straight line y plus 4x is equal to 2 because its slope is minus 4, and minus 4 into 1 by 4, the slope of the electric or the gravitational field, will be equal to minus 1. That's the required answer. And which is the option that satisfies the result here? Yes, sir, it is option A. 2-point masses m and 2m are placed at points A and B as shown in the figure. E represents the magnitude of the net gravitational field strength. Net gravitational field strength, keep that in mind, as we move from A to B. Option A, E will first increase and then decrease. Option B, E will first decrease and then increase. Option C, E decreases throughout the journey from A to B. And D, E remains constant. So how do we attempt a solution? Let us have a look at it. So here is the system, two masses m and 2m at A and B, and we are looking at what happens to the net gravitational field strength magnitude. We are not interested in direction at all. Magnitude is what we are interested in. So what happens to that magnitude as you are moving from point A to point B? Now let me bring to your notice the fact that these two masses will have a point in between them along the line joining them. Let's call that point as point P, at which the net gravitational field is 0. We will call that as the null point. So here the net gravitational field Eg will be 0 because if I place a plus 1 kg mass at P, 2m will attract it with a field E2, let us say, and m will attract it with a field E1, let us say. So I am considering that point P. Obviously E1 and E2 are opposite to each other, but the point P I am considering is that point at which their magnitudes are also equal, right? So the net gravitational field will be 0 because these two are equal in magnitude and opposite in direction, and they cancel out. So there will be one point wherein the net gravitational field somewhere in between m and 2m will be 0, and that point is P. Now let us discuss as to what will happen at points A and B. So now what will happen at points A and B? At A, the field due to B will be some g into 2m by the distance between A and B, call it as d. So gm by d squared, correct? And what is the field at A due to m itself? It is gm by distance of m from A, but m is at A, so the distance is 0. So I'll get gm by 0 squared, which is infinity. So the field at A, because of m, is infinity. Of course, the other field is finite, but then you're adding something finite to infinite, it will still remain infinite. Agreed? Now what happens at B? Similarly, the field due to m will be gm by d squared, right? And the field due to 2m will be g into 2m by 0 squared. The distance is 0 because again 2m is at B. So 2m contributes an infinitely strong field at B. So at A it is infinity, at B it is infinity. Somewhere in between them there is a null point at which the net gravitational field magnitude is 0. So what is actually happening to the magnitude as you move from A to B? Well, at A it is infinity, then you move from A to P. When you move from A to P, it is decreasing from infinity to 0, obviously, right? The magnitude. We are not at all discussing about direction here. Now, from P to B as you move, at P it is 0, at B it is infinity, so it is increasing again. So the answer is, it first decreases, becomes 0 at some point, and then increases. So which is the option that matches with these arguments of ours? It is option B. E will first decrease and then increase.